give me a chance to talk to you a little bit on resilience of complex systems from an engineer's point of view. I'm sure resilience has been a discipline in research for decades. It is very young as the interdisciplinary research discipline that we now see on complex socio-technical systems. And that's why I see it so important to learn from each other, to find out where the perspectives are and how we best integrate our disciplines. So resilience addresses key aspects of the way we as societies and different societies around the globe live and how we can manage disruptive events. We know we are susceptible. We know we can't totally avoid being hit, be it natural disasters, be it technical problems, terrorist attacks, all kinds of disasters happen. And yes, we know we are vulnerable. Those adverse effects end in damage. And we see that we have to face casualties. People are killed by those disasters. That's why coordinated action is so important. And that's why we have to look at those events with the perspective of our specific discipline and to learn from it in order to be better prepared next time. So those adverse events and the consequences we have to face are the basis for preparation for the next time. And here in Freiburg, my colleagues at EMI published a short and compact definition of what we engineers understand with resilience engineering, mean it that we try to preserve our critical functionalities, ensure a graceful degradation, not a too abrupt one, and enable fast recovery. So that's a combination of core capabilities of a system we seek that allow the system to overcome those disruptions. And the help of engineered generic capabilities as well as customized technological solutions are our interest when the systems witness those problems. That's why we see resilience as a topic that we best manage in a cyclic way. That as researchers in civil security establish ways to prepare for a disruptive event, to protect systems against it and to try to prevent it even, is one component. But we know disasters happen. And when it happens and causes damage, we need two additional factors that are core to resilience. That is the capability to fast, immediate response and to recover as soon as possible. And with this new understanding of the system, we can learn and adapt. So this one image of Puebla Earthquake may not be quantitatively applicable to the cycle, but we know in '85 we had in Mexico City an earthquake killing 10,000 people. At least part of we observed there and learned from may have helped to see a lower number. Still, 370 people were killed in this most recent earthquake in Puebla and near Mexico City. So if we start looking at resilience in this way as something we can adapt to in a cyclic process, an engineer's perspective means we have to advance our tools, we have to use what we are used to apply if we want to solve a problem. If we want to preserve functionality and ensure that a system is available across a disruption, we need data. Engineers need to know what the specific properties of the systems are. We need those data for metrics and quantitative measures for the system, to derive standards, how to build or rebuild systems in a specific design. And as I think, it is very important to have models for simulation of systems in a way that we can find a optimized solution. But of course, this is only one perspective. I mentioned it a couple of times. We have so many disciplines involved, but we also have many stakeholders. And that may be another type of complexity we face in resilience research. Of course, we have the interest of societies. We need to find acceptance for whatever we plan and design and construct in order to make a system more resilient. And it will only be done if it is of economic value, if there is cost efficiency. Otherwise, no entrepreneur will take money and invest into it. And politics need to see an advancement. They need to see that we can be better prepared for the next disaster, that we as a society have a benefit of it. And of course, academia has various disciplines that are interested in it and that have their own views on it. And some of you may disagree with my descriptions and wordings. I experience that is normal to such an interdisciplinary approach. But the more we talk about it, the better and the sharper is our understanding of it. So I mentioned this economic value. And to this I relate that it must save costs at the end if we take a new design or a design that integrates resilient capabilities. With those aspects, we have new and additional data that we have to take into account as an engineer. The metrics that we use shall provide an estimation of the level of resilience we actually have in the system. The models help us to simulate and to find it with regard to economic value. And the question is, does it really pay off? Is the new design, is the integration of resilience as a concept really cost efficient? We have people in this room like Michel Bruno that developed metrics and showed us how to measure the resilience of a system. An important part is a performance time history graph, just plotting how much of an expected performance of 100% is available. And we know after a serious disruption, it drops. And over time, we hope that it recovers and reaches finally, at some point in time, the expected value. If we relate this to a physical value like power, we find that this integral that is lost is a lost work. And of course, in parallel, we can plot over the same time the costs it takes to respond, to re-establish a system. So those are numbers we can deal with. And we can use this in a process where, as an engineer, I look at the critical infrastructure I'm interested in and I want to find a new design for. I have to formulate it a specific scenario, a certain earthquake, a certain natural disaster type, and start calculating. How does the system behave under this scenario's loads? And with this, I find, yes, I will see damage, and I will see work loss, so downtimes. I can calculate them, establish those numbers. And then comes a point where we at least have a cost analysis, a damage analysis. Maybe if we do have information on the probability of this scenario to happen, we even have a risk number. Maybe, maybe not. at least we have a number that we can communicate with people who have to finance it and tell them it costs you this and that amount of dollars to make your system more resilient. Maybe we have even a risk value, a combination of the damage and the probability. Then it is maybe the topic of a reinsurance or an insurance company. Here is an important point of the discussion, as I realized in resilience engineering. Who's leading now the game? Is it a risk topic? Is it a resilience topic? Is it integrated? Where are the links and where are the thresholds? Which way ever, society will decide this is a risk or a number of people killed, I accept. We do this every day when we take our car and hit the road on German autobahns. The entrepreneur also does it every day. Every day, the decision must be taken, do I invest in a specific path or not? If we look closer at the measures we have, we need to find out which measure exactly. And if we do it in more details, we find it is not that one-dimensional. It is not only one scalar we derive, and that is sufficient to give a precise metric of the system's resilience. We see that maybe we have a redundancy, and the same scenario happens, and we have no downtimes, we have no damage, so it goes on. But this one disruption that takes use of a redundancy also means we have no second redundancy. For the second hit, we have no redundancy anymore. So factors like this is just a simple example, are important to take into regard. And it is, as some recent papers show, much more complex than just this one-dimensional scalar value that we have to take into account. Now, an important point for an engineer to use those measures is its predictive capability. How precise can I predict what will happen, how big the damage is? And that's why I see some limitation in the way we now measure the resilience of a system. Yes, it is a measure if we observe it ex post, if we see what happened. To go a step further, to have a prediction of the capability of the system to overcome disruption, we need more. We need more in this process where we establish metrics. To one point in terms of the metrics itself. So I think it is much more complex than in the first start we see. And we have another complexity, that is when we define the scenarios. We define a specific scenario or even a variety of, but then a disruption happens that is different again. And the system behaves different than what we expected it. And that's why we have uncertainties in the system. And the combination of those uncertainties in the scenario and the limited predictive capability of the metrics is what I think a lot of in our research here. And that's why I think that development and application of models is so important, of models allowing us to simulate the system. For once, because the models are able to predict expected damage, predict the metrics we have just seen, but we can vary in the models the scenario and the behavior, the properties of the system. So if we are sure that the models contain enough of the physics of the systems, for instance, it has a satisfying predictive capability. And if this one component of damage prediction is attributed by a second one on formulating potentials to recover, to respond and to recover, we can predict what we so far call the metrics, the measure of resilience. And it has a second opportunity, modeling the systems. We can start describing what happens to a system starting from what might be damaged. So to describe the damage in the system provides us some independence on this uncertainty of which scenario really happens. So if we assume specific components of the systems or the systems of systems are damaged, we can start calculating what is going on to happen. How does this certain specified damage scenario influence the rest of the system? Do we see cascading effects? How does it propagate into other parts of the system? And if we change it in the simulation, if we change the component that might be damaged, how does the new type of system, the new design behave? Thus, we can again do a kind of optimization and reach information that is predicting the behavior of the system under various damage situations. And even from the combination of amount of damage and costs for response and recovery, derive metrics and quantitatively assign a level of resilience to the old and potential new design. Including the costs means we can talk to economists and say what the needed amount of money is to make the system more resilient. We have then some more reliability on what happens. Still, we get not rid of the uncertainty as such, because we will never be able to 100% cover all potential kinds of damage. So it is only a part of the solution, but a step into the right direction, as I think. In one of our projects at EMI, we address this problem, and in the CSAR code, we simulate cascading effects in coupled grids, in grids of water, energy supply, and communication. And in those models, we implement damage scenarios. So we say that specific components of one of the grids or multiple grids fail. And then we simulate what happens to the specific component in one grid, the behavior of this grid, and the interaction with the others. So it helps us to analyze how resilient is this combination of three different networks. How do they interact? And if we simulate those integrated grids, if we use this information to calculate the amount of total damage, it is only a matter of integrating more information, like how much time and money does it need to recover in order to calculate the full metrics and to predict the resilience of the existing system and the one of a maybe changed one where we identify a hotspot that causes the biggest grid-wide and intergrid-wide damage. So in a way, mirrored back to our resilience cycle, this approach of defining damage scenarios is a way of working counterclockwise. We plan with the consequences in mind in this context and at least get a little bit free of the uncertainty we face so often. Here in Freiburg, we have the four institutions that were mentioned. That Fraunhofer EMI was the local seed point for resilience engineering, and we heard it earlier this morning that the University of Freiburg started a close cooperation with the 5 local Fraunhofer institutes formed this sustainability center, and within this the engineering core of the Department for Sustainable Systems Engineering, where we exactly do also the resilience research. And our topics at EMI are very much addressing those simulation components. So we developed software tools for urban resilience. We try to model those interdependent grids, addressing the different phases of the resilience cycles. We are, of course, aware that simulation is only one component, and we are happy to have internal capabilities and many colleagues in the engineering faculty to develop, for instance, new sensor types. We need precise information of what happened in the location we have seen the disruption. We need reliable information on physical data, and we need it whether we have energy supply or not. So we developed energy autonomous sensors to be implemented in tunnels or in other building types where we might see catastrophes, including fire, high temperatures, pressures, gaseous, toxic environments, and have information, for instance, for the first aiders, what's going on inside. So providing data to be able to best plan the response activities. The damage assessment is, of course, extremely important to best quantify the situation. In terms of protecting structures, we apply our specific civil engineering competences to develop retrofit for existing structures and to also test critical infrastructure components on a civil engineering basis, for instance, towards the behavior under blast loading. So we are able to investigate the behavior of whole facade structures, windows, doors, big panels under detonation effects, and make such critical infrastructure components better prepared for that type of disruptive situations. And that led, for instance, to modeling systems like urban environments, urban situations where we have totally different combinations of buildings in a city, a compact city, a very dedicated parts with dedicated sectors for specific use, then central business districts, for instance, and they, as we see, behave differently under the same type of scenario. And behavior means here how is the building's usability in those types of cities over time if we have a specific disruptive event. So how graceful or not is the drop in its usability? How long does it take to rebuild and to recover? And what does it cost? So a very civil engineering approach deriving those performance time histories for the buildings, enabling to estimate the resilience of whole quarters in a city. This, as we think, is only a first part that addresses preparation. We are convinced that such numerical tools to assess a combination of buildings in a city can be expanded by tools that allow us to do real-time analyses. So to use the information provided on the current situation for planning response. And in a third step, we of course want to integrate the component of what have we learned from former disruptions, integrating it in planning for the future, cooperating with urban designers, urban planners of future structures. One example on our point of view for the future of applying, of using that kind of tools for simulation. Now, if I see, as you showed me in the beginning, the combination of all different disciplines in this room, I of course have the expectation to this summit to integrate it and to find ways of exchanging the different point of views. From what we have done at EMI so far, I see that it is important to find out where the selling points of resilience engineering are. Otherwise, it will lead to nothing, just a few academic findings. I want to find out where can we do something? Where is the interest and need on the industry side to develop new solutions and new tools for support? And in this respect, of course, we are looking for partners to co-develop those tools. How can we do this under the specific type of complexity we always see in resilience problems, and which disciplines are here to talk to engineers to find out how the other boundary conditions to the problems are in order to successfully address them. And how do we mutually integrate different disciplines like risk and resilience in the context of, at the end, achieving the best result, the best design for future of our critical infrastructures. With this, I thank you for listening to my introductory talk, and I wish us all a fruitful and successful summit over the next 2 days. Thank you very much. Daniel? Yeah. Questions? We have microphones in the room, so please feel free to start questions, discussions. Yeah, Herr Heinemann.
Just one question. How far does risk management go, and where does resilience engineering start?
Thank you for posing my question again. Yes, this is exactly a problem I have no final answer to, because I see an absolute necessity of doing many parts of what we do in risk for resilience. I want to know what is the expected damage. I also want to know the probability, to know how significant is it, how much is the need to act. And if I understood some of your talks correctly, it is not always given that the highest probability and the highest risk is the ones we have to put the biggest focus on. In resilience, I think, at least to differentiate it a little bit, in resilience we address response and recovery. So that I think is making a difference. But maybe you see it differently. That's what I learned in resilience engineering makes it so important as a new discipline, or as a new context for a new concept for engineers, that we go beyond this prepare, protect, prevent, that we start thinking of response and recovery. Maybe this is also a point in relation to existing and developing risk research, but please correct me if you see it differently. Hiermaier?
One question, how far are your thoughts about modeling risk scenarios away from what we actually see in the risk management in existing structures, in existing infrastructure management? How far is here the theoretical thinking about risk management away from what we see in practice?
The distance always depends on the quality of the data we have. That's what we see when we do quantitative risk analysis. It is strongly depending on the quality of probability data. And this is different with respect to different scenarios, different structures, different loading conditions. As far as the second component of risk is concerned, the damage, we have many tools, experimental ones, numerical ones, to measure or calculate the damage. The critical part in the quality and how close we are to reality, to my point of view, is always primarily the probability part.
Stefan, I want to challenge you for a moment with your response to this very important question. Yes. Because when I hear it depends on the quality of the data, where I was going with this question was actually it depends a lot on the political and social context. So if you could just basically reflect on that tension that is emerging here a little bit and how you see the kind of work that you are really proposing. I think you very consciously chose counterclockwise thinking as a way of disrupting some traditional ways of thinking about disaster and recovery. So I'm just curious how you would respond to someone like me saying, no, it's not the data, it's the politics. And of course, I'm over simplifying there. I do recognize that as well.
Mm-hmm, mm-hmm. Okay. The data will be the same, I would expect, independent on the politics. But of course, the influence on how we weigh those data, maybe how we filter them, has a huge, tremendous influence. So I am not the one to determine the objective set of data, but this is of course used. And if you apply different point of views to the same set of occurrences, of consequences in an observed situation, different institutions, different political approaches will count differently and thus providing different data. Is that what you mean? Yeah? Yeah, yeah. So it is very much depending on the local cultural setting, on how you count the numbers of whatever. And on top of this, of course, comes the perception and the assessment of it. So, simple example: casualties in traffic. Yeah, how is it weighed, and how is it illustrated and used? I cannot answer this question as an engineer. I have to take the data as they are, but I'm fully aware I need partners telling me how to weigh the data and in which way to see them. Does this answer the question a bit? Yeah.
Yeah, I would like to come back to the question of Professor Heinemann regarding risk and resilience. In fact, in many past projects at Fraunhofer EMI, we started out together with the social scientists to find kind of processes for a kind of joint risk and resilience assessment. And it turned out that it's very critical and for success of the project and also for scientific outcome to find a kind of set of methods that accompanies this process of risk and resilience assessment and management. So that, for instance, for the identification of potential threats, we use roundtables and tabular approaches. Then for the performance function identification, we use kind of strong feedback from end users, what they really need, for instance, level of service of the electricity grid. However, for the real simulation and engineering assessment, we have to go deep into the models and the modeling and into kind of generating predictive capabilities. And I think this combination of going from making up a roadmap together with stakeholders and decision makers, then selecting the right methods at the right steps, and then going deep, zooming down into the engineering stuff and doing predictive modeling, I think this is critical for overall success. And we saw one such flow chart by Professor Hiermaier with this nice roadmap he showed over and over again. I think this is kind of a type of comment, a lessons learned we have from many projects.
Steve, you had one more question.
Yeah, I want to maybe continue to drill down on this in part because this is really animating why I think we have the group here. This data issue is a real challenging one when we're talking about complex interdependent systems that have essentially different geographies, right? If we're looking at water, if we're looking at transport, we're looking at health. And so getting access, though, also sprawls between the private and the public. Right? Because much of the infrastructure is privately owned, or there may be public ownership across these jurisdictions. So the formula for what can feed into the data is what there, but getting access to the data, I want to particularly get at the private-public issue. How do we get the sharing in order to get to a point where we have robust simulations of robust models?
Mutual trust, and there must be a need. It must be necessary. If I look to other research institutions, sister institutes in the Fraunhofer Gesellschaft, where primarily mathematicians work on solutions for whatever kind of topic, I see that those mathematicians get into the very core of enterprises. They show them exactly what they do. They show them their precise numbers because they need solutions. So there must be a pressure, a need for a solution. Then we get data. There must be trust. We need to be partners for the ones who need solutions. This is an ongoing process. We need to show that what we do is providing reliable, applicable results. And we have to show it's useful, it's cost efficient. And we will, for some applications, find it's not. And then we also have to tell it. So this honest exchange of information is a precondition to get more and more data on real behavior. And for some sectors, we will not get data maybe. Okay, it can also be, but it is a process of exchanging information, of showing what the capabilities are, what the improvements maybe are, and thus a give and take. We see this in other applications as well. So also here it is very, very complex maybe. Yes.
Thank you. I want to go back to the point that Uta was raising, because I think there's a lot of potential in the tension that she identifies for us to really be forward-thinking and truly transformative. And I sense that this is going to continue to be an undercurrent as we go forward. In our program, our project and vision in the Caribbean context, obviously, we've been resilient in terms of the devastating storms and the hurricanes since the beginning of time. But we've also been particularly resilient since the great disruption of 1492 and the landing of Columbus and everything that has come since. So in many ways, we're tired of being resilient in some ways. And if resilience is going to be focused only on the infrastructure and the preservation of certain traditional ways of doing things, maybe we have the opportunity also to think about the truly potential transformative ways of approaching resilience in a broader social and political context.
Absolutely. That's why it is so important to have different disciplines here talking all about resilience.
Yes, and it's a straight relation with the comment of Professor Buscalia, that it's very important the behavior like consumers that we have, because the resilience is the answer of a behavior that we, in the last 1,000 years, we have in the human being. But how we'll approach the next of our behavior like consumers. And after that, we have to be very clear what sense of prosperity, what it's for us to be prosper, you know, because we are talking and we are approaching a lot the answer, you know, the post phenomena.
Yes.
But that phenomena was being happened in some part because of us, and I think that we have to open both sides after phenomena. And before that, how we'll be changing our behavior like consumers. You know, how we'll be changing that.
Okay.
And our sense of prosperity.
Yeah. Thank you. I see one more question, and then I think we go for the coffee break, correct?
Jens Holst from Siemens. Just one question on the business perspective. You spoke about the selling points of resilience.
Yeah.
Where do you see these selling points today? And do you think that new business models could also be applied? And what are your ideas about that?
Yes, absolutely. So if you think of whole new technological chains that are rising, like autonomous driving in automotive, we will see even more need and opportunities for implementation of resilience in technological solutions. This will, of course, address specific topics like functional safety, like artificial intelligence in a totally new way that not only provide customized behavior of the system, that not only provide comfort and real-time solutions, but also more resilience of the system, specifically addressing the prepare and prevent phases maybe, but potentially also everything what comes after. And we see in industries like information industry, Google and Amazon, for instance, huge interest in resilience with respect to how to deal with disruptions. They made their own internal concepts on how to deal with it. For once, with the technology, when they use game days and simulate damage in whole clusters of their server plants, and in addition to the technology, of course, the behavior of people working with it. Being faced with find solutions in the system on time, in real time. So there I see major opportunities to establish and to integrate more resilience capacities in the near future. Thank you so far, and I think it's time for a first coffee break now. Thank you.